Recall that we have been solving exercise 3 which we did not solve fully. It asks us to prove this proposition. We have so far proved the first 4 parts of the proposition A, B, C and D. So today let us see part E. X as usual is a metric space. Now if E is a subset of X, then this part tells us that E is open if and only if the complement of E in X is closed. We write solution in place of proof because we are solving an exercise. Let us first note these facts. Since interior of X difference E equals exterior of E and exterior of X difference E equals interior of E, so E and X difference E have precisely the same boundary. How are these two things true and how are we concluding this from them? Let's try to understand that first. I will write this explanation separately between dashed lines because I don't think it deserves this much of elaboration. It is something that is pretty easy to see and you can just write the rest of the proof from here itself. But for our own sake and for our own understanding, we are adding extra details. Let us first take this identity and see how it is true. So what we do, we have two sets here, interior of X difference A and on this side we have exterior of E. Let's first try to show that this is a subset of this. So we take any element X in this interior, but then by the definition of interior of a set in a metric space, I mean this means that X is an interior point of X difference E. By the definition of an interior point, there exists a positive real number R such that the ball centered at X having radius R is entirely contained in the set whose interior you are considering. So that means this ball is a subset of the complement of E in X. But then the ball does not intersect E at all because it's sitting inside the complement. And the complement of E and E themselves are disjoint. So if something is totally inside X difference E, obviously it will not intersect E. But then by the definition of an exterior point, X becomes an exterior point of E. So X belongs to the exterior of E. And that's how this is a subset of this. Similarly, exterior of E is also a subset of interior of X difference E. To prove this reverse inclusion, you can carry the steps backwards. Okay, you will see that they work. And that is why we have this identity and similarly we have this other identity as well. Now how do they imply this? To see how we can conclude this equality from these two, we take any element X in the boundary of E. That means X is a boundary point of E. So by the definition of boundary point, X is neither an interior point nor an exterior point of E. And that is why X does not belong to the interior of E, which however is equal to exterior of X difference E. And X also does not belong to the exterior of E, which is equal to the interior of X difference E. So you see that X is also neither an interior point of X difference E nor an exterior point of X difference E. And that is why by the definition of boundary points, X belongs to the boundary of X difference E. So that way this is a subset of this and you can also prove the reverse inclusion. So that is how you have this equality. I am not erasing this part because this is our main proof. So I have been writing the explanations here. So now we can continue. Hence, we have these double implications. Let's start with the statement E is open, whose meaning is just this. This is coming from the definition of an open set, that E does not contain any of its boundary points, that the intersection of E and its boundary is empty. But just now we have proved that that is just equal to the boundary of X difference E. So that also does not intersect E, there is no common point. But that itself is equivalent to this condition, that if it is not intersecting E, that means it's lying entirely outside of E or inside X difference E as a subset, which however is the definition of X difference E being a closed set. So that is why E is open if and only if X difference E is closed. That is the proof of part E. Next we have part F. E1, E2 up to En, these are open in X. If so, then their intersection is also open. And if finitely many sets are closed in X, these Fi's, then their union is also closed. We can state these two things like this: the intersection of finitely many open sets is open and the union of finitely many closed sets is closed. In the solution, let us first show that this intersection is open, and keep in mind that each EI is open. So we take any point X in the intersection, we have to prove that X then is the center of a ball with some radius that is entirely contained in the intersection. Then the intersection will be open by one of the previous parts. Now, what does it mean for X to be in the intersection? It means that X belongs to each EI, but each EI is open, so for each such EI there will exist a positive radius, say Ri, such that the ball centered at X having radius Ri is entirely contained in EI. Now you have got how many radii? N number of radii. You take their minimum, because each one of them is a positive real number, so there will be a minimum because finitely many of them are there, and that minimum, let's call it R. Obviously that is also positive. Now it's pretty easy to show that the ball centered at X having that minimum radius R is contained in each EI. Actually this is how you have to show it, that this ball will be contained in B of X comma Ri for each I, which itself is contained in EI, so that way this will be contained in EI. This part I am leaving to you, you have to prove this. But then what are we getting out of this? From all these inclusions, you next get this, that the ball is contained in their intersection as well, and that is why we are straight away writing that this is open. However, exactly how is this open? I mean, how can we draw this conclusion from this? What is it that we have shown here? We have shown that X is an interior point of the intersection, but originally X was any point in the intersection. This means that this set, this intersection has all its points as its interior point, or in other words, that this set is a subset of its own interior. But we know that the reverse inclusion is always true, that the interior of a set is a subset of the set, regardless of whether it's open or not. So that means the set is equal to its interior. And now you go back to one of the previous parts of the proposition that we are proving, that tells us that it is precisely this condition in which the set becomes open, that it becomes equal to its interior. That is how we are drawing this conclusion. Then we go to the next part, which asks us to prove that the union of the closed sets Fi is closed. We start like this. For this one, we do not have to consider elements or anything. We are going to use whatever we have proved so far. Each Fi is closed, that is why the complement of each Fi in X difference Fi will be open by the previous part E. And that is why, because now we have finitely many open sets, these complements, by what we have proved above, that means this fact, the intersection of all these complements will be open, which however by De Morgan's law is the complement of the union, extended De Morgan's law. Okay, but now, so now we again apply part E to the fact that this complement is open. So its complement will be closed, which is nothing but this union. So that's how we have the proof that the union is closed.